In this video, we present our work on learning visuotactile affordances for cloth manipulation with local control. As humans, when we manipulate long cloths, like a towel or a bedsheet, we often want to grasp the cloth by the corners. But how do we get to the corners? We might use vision, but the corners are often occluded. Many researchers place the cloth on a table and then incrementally move parts of the cloth until the corners can be found. This can be slow. Alternatively, the robot can suspend the cloth in the air and slowly rotate it, using computer vision to find the corners. This can also be slow. In addition, the corner may not be directly graspable. This is when sliding becomes particularly useful. Our system can pick a towel from the ground, grasp a corner, and then use a novel visuotactile grasp affordance network in order to grasp an edge. Once the robot grasps an edge, it can slide along the edge under tactile control until it finds the corner. Once it grasps the corner, it can do other tasks, like unfolding and folding. We'll be discussing the 3 key capabilities that are necessary to generate this complete behavior. First, tactile perception of local features for tactile sliding and grasp supervision. Second, our visuotactile affordance network for grasping edges. And third, tactile sliding. Our visuotactile affordance network takes a depth image from the RGBD camera's input and outputs an affordance image. The red colors indicate locations that are predicted to result in a successful edge grasp. We train this network using tactile supervision. The robot attempts a grasp, and the tactile image indicates whether an edge was successfully grasped. Once we've grasped an edge, we can slide to the corner. We demonstrate sliding in 2 configurations, downward, and the more challenging horizontal configuration to demonstrate how sliding can be used for longer towels. Starting with our tactile perception networks, in order to slide, we use tactile perception to estimate the pose of the towel edge within the grip. This network takes a single tactile depth image as input and outputs the grasp state, including whether or not an edge is being grasped. Here is our network in action. It runs at 33 Hz, and you can see it's robust to wrinkles on the sensor's gel surface. We also have a separate tactile perception network with similar architecture in order to supervise grasp attempts. This network needs to distinguish between edges and folds, which can look similar. We improve the performance by using multiple sequential images to capture temporal information. This network can also identify direct corner grasps. Here we show our network classifying between an edge, all fabric, a corner, a different edge, no fabric, and folds. We augment our datasets for both networks by taking a label training image and randomly varying the maximum depth. Then, we add random translations and rotations. Our pose dataset consisted of 150 hand-labeled training images, which we augmented to 30,000 images. The grasp supervision dataset had 330 grasps per category, which we augmented to over 6,000 per category. Now, let's move on to the affordance network to find the best edge grasp point. In simulation, we can label the entire image, but there's a sim-to-real gap. On the real robot, we can only test one grasp point at a time. Our method uses both strategies. We first train in simulation, and then fine-tune on the robot. The affordance labels can be calculated in simulation, because we have access to the full state of the cloth. Good affordance occurs when the cloth point is an edge, is just a single layer, and can be grasped without collision. Then we fine-tune this network on the real robot. Instead of explicitly checking all the labeling criteria needed in simulation, tactile supervision tells us if an edge was successfully grasped. We collected 3,000 grasps for fine-tuning. Here's our affordance network in action. It's able to distinguish between edges, as well as folds, and cases where the gripper would collide with other cloth regions or grasp multiple layers. Here are examples when the entire right edge is graspable, the right side of the image is actually a fold, and cases where the edge is twisting such that only parts of it are graspable. In this one, only the top half of the edge is graspable because the bottom twists in on itself, creating a fold. In this last case, the surface normal of the cloth is only aligned to the gripper at the bottom. We compare our network to 3 other baselines. The first is based on work from Chen et al. That takes a depth image as input and outputs the segmentation of the edges. We also consider edge uncertainty, reachability, and surface normal alignment with the gripper. This approach can't identify grasps that would fail due to collisions with other regions of fabric. Next, the sim-to-real network, transferred directly without fine-tuning, often misses grasp opportunities and will complete a full rotation without successful attempts. Lastly, the reel-to-reel network, which is trained directly on the 3,000 grasp attempts, is more likely to grab inside the cloth without the underlying structure we get from simulation. Ultimately, our network outperformed the others on both our offline evaluation set and during real robot deployment, requiring fewer grasp attempts to grasp a real edge. Now moving on to tactile sliding. We have tactile sensors on both grippers. The pose from the sliding gripper informs the controller whether to move forward or back to move the edge towards the target position. When the other gripper feels an increase in shear, the robot knows it reached a thicker corner. Because of our high-resolution pose estimates, we're still able to slide to the corner even in the presence of disturbances. Here we show tactile sliding in the more challenging horizontal configuration for longer towels, where it's more likely to slip out of the grip due to its own weight. We learn a dynamics model and use an LQR controller to choose a pulling angle to keep the edge close to the target position. Now that we can grasp adjacent corners, we move on to folding. Since we know the size of the towel, we can do tasks like folding open loop. Visuotactile feedback could be added to accommodate towels of different shapes and sizes. And finally, to sum up our key contributions, we've developed tactile perception systems for estimating the pose of the fabric edge for tactile sliding, and classifying grasp types to tell if we've successfully grasped an edge or not. We also introduce a novel visuotactile grasp affordance network for grasping edges, and develop tactile controllers to slide along an edge both vertically and horizontally. And ultimately, we demonstrate how all of these components, using visual and tactile perception and control of local features like corners and edges, can be used together in a cloth manipulation system for tasks like unfolding and folding.